Yeah, sorry.
You have become an X-Men now.
Yeah, an X-Men. Yeah, that's right. With superpowers. He comes out now flying. Okay? So we have a machinery to generate different scalars.
So that means that this capital R is playing a major role.
What?
Capital R
Yeah.
is playing a major role.
Yes, it is, because capital R is the radius of the orbits.
And it's changing all the time.
Yeah, it is the same for a given orbit.
Yeah, for given orbit.
But then you change orbits and it's, yeah. R is this quantity R, big R, is very important
Yeah, very important.
in spherical symmetry.
Yeah.
Now, we go out of spherical symmetry, you can do all these things, but then the covariant meaning may be lost. And this is an open question, whether you can still do it. Now, spherical symmetry, no problem. That's it. Now, the question is whether these objects are useful or not. Because you can generate these objects and maybe they're useless. Like, which scalars do you think that should be subjected to this? We've already seen that rho goes to rho q, which is simply m by we've seen that if we subject rho to this definition, we get something like this, which is very nice. Because this is the quasi-local mass divided by the quasi-local volume, right? And that's very nice. But as far as now we're concerned, this is nice. But which other scalars would you suggest that should be subjected to this procedure? Like, which other covariant scalars are there around?
Hubble constant.
What?
Hubble constant.
The Hubble, no, not the constant, the scalar.
Scalar.
The Hubble scalar, which other?
Sigma, capital sigma.
The sigma, for example.
Okay.
The expansion, he said already.
Shear.
The spatial curvature. The Ricci scalar of the, yeah. And the psi 2, why not? The sigma, right? So there are a bunch of scalars that can be subjected to this. Even R itself can be subjected to it. It's interesting to see that R goes to RQ. What is RQ? RQ is R squared R prime dr by this below will always be, the thing below in the denominator will always be 4 pi 3 RQ. But then this, notice that this becomes the integral of RQ R prime dr. And this is 1/4 of R4, right? Yeah?
You have to multiply 4 pi in the numerator also.
Yeah?
4 pi
In the numerator, yes, that's true. That's true. Yeah. Okay. So this is pi. And this is 4 pi 3 R2. This is 3/4 R. Yeah. R. Maybe that's not useful, but it can be done. It can be done to any scalar. To any scalar, you can generate a cosine or a product that will be like this. So let's start exploring these possibilities. Okay, so okay, notice that again I emphasize the proper density, average distribution, has no simple analytic form. We can't integrate this. We can't, because this factor, essentially, we are integrating over this. So, and we know that this is the mass, right? But here, well, what we can, the only thing we can say, if we work with a proper volume, is as follows. If we work with a proper volume, that means we would have to put square root 1k, and here square root 1k. The only thing we can say is that this is the proper mass divided by the proper volume. That's all we can say. And then this would be rho p. This would be the average density, the proper average density distribution. But we have no simple analytic form. Here we have a very simple analytic form, right? Okay? Well, let's see what else we can do with this. Okay, quasi-local scalars. All scalars I can obtain in this form, we will call them Q scalars, right? We have the scalars that we've been working with. These are like, say, the normal scalars, right? The usual, the standard scalars. And from these scalars, we're going to construct Q scalars, right?
Maybe before we start this, I have one question. Of course, I understood, but half understood. That, okay, but that quasi-local mass,
Yes.
it's for a fixed orbit, R star.
Is what, sorry?
It's for integration for fixed orbit,
Yes,
R
yes.
equal to R star.
Yes.
And the proper mass, proper M,
Yes.
MP,
Yes.
that is for means in flat case it will reduce to quasi-local mass.
Yes.
Yeah.
No, they both reduce to the same.
Same, yeah, that means they are equal.
Yes.
Otherwise, no, in general it is not.
They're
equal.
not equal.
I
General,
don't know how you can understand means what is the physical meaning of that is not clear for me, for proper
yeah,
mass.
well, proper mass is like, is a different, because similar things occur with distance. You can call R. R would be the area distance, okay? So how do you measure that? You say there is an orbit. I really am measuring area. It's an orbit. But I take distance as the square root of that orbit, right? And the proper distance would be if you take small accumulative measurements, right? The proper distance would be measured. The proper distance is an integral over a curve, right? So that means that you are adding small bits of distance, right, until you reach the orbit. See, this is the physical meaning of proper distance, right? The physical meaning of area distance, you don't do that. You take the surface and you take square root of that surface. See? The area distance is a quasi-local quantity because it depends on the area, right?
Yeah.
So you evaluate the area, but you never go slowly like this, like this, like this,
No,
like this.
yeah. Yeah.
So it's the whole area, you take the square root, okay? And then you have the area distance. Now, the proper distance is the integration of all these segments, right? All small segments, you are adding them up, okay? In flat space, it's the same. In flat space, it's the same thing, because the metric is flat. So it's simply trivially adding all these segments. See, it's the proper the proper distance along one curve from here to here, right, is the integral of the metric, right?
Yeah.
Let's say the space metric, right?
Yeah.
How do you call this? Arc length. It's the arc length.
Yeah.
It's the arc length. So that's it. So you need to know how J is changing everywhere, right? Now in flat space, this reduces to the integral of x dot, well, let's say dx by d lambda squared plus dy by d lambda squared plus dz by d lambda squared d lambda, right? This is simply the proper length, right? But then this will be exactly the same as the square root of the area, right? You take a sphere around that, and you take the square root, and it will be the same, right? In flat space.
In flat.
But in curved space, where the metric is no longer constant, then this is an integral that is weighted with a metric, right? It's going to be different from the square root of the area. This is one of the effects of curvature, right? In fact, even in very small curvature, I mean not very small, very simple, like the surface of the two-sphere itself. If you compute the arc length from the North Pole to a certain meridian, to a certain point in the sphere, this is going to be different from the radius of the sphere. Try this exercise. You start in the North Pole and you go latitude 45 degrees along a meridian, right? Okay? And compute this distance. And you will see that this distance, no, but it's not the same. It's not the same idea. No, it has to be done in three-dimensional space. No, in 2 dimensions it has to be defined differently. But the point is, no, yeah, probably the case of to make it work on the sphere, you take, this is a two-sphere. You start in the North Pole, and you compute this integral, right? You compute the arc length here. And then take the area, take this area here, the area of this section of the sphere, and take the square root of this area. You will see it's different, right? But in the flat space, no. Flat space is the same. Okay? So this is one of the effects of curvature.
So there is mainly effect of curvature, which is giving you MP and...
Yes. It's a curve, it's an effect of curvature.
Could it be said that the observer inside the Schwarzschild surface will observe proper mass and one outside will observe quasi-local mass?
No. No. The quasi-local mass is what Schwarzschild observers observe everywhere. That doesn't matter if they're inside or outside the horizon. Okay. What happens is that inside of the horizon, they have to fall. They cannot escape, that's all, but the mass, yeah.
So, I don't understand, why do we need the quasi-local mass when we can calculate the proper mass?
Well, no, we need it. The test, whether it's needed or not, is how useful it is. You can say, why we need the GR if we can calculate things with Newtonian physics? Yeah, you calculate anything with Newtonian physics. Why do we need quantum mechanics if
But Newtonian,
classical mechanics works very well?
but in case of Newtonian, it is an approximation. Here, the quasi-local mass is an
No, but no. But why do we need to study a gas with kinetic theory when we can do it with thermodynamics? Why do we need to bother with kinetic theory? Well, you can say because kinetic theory looks at the microscopic things. No, these things, you try new concepts, you invent, you have new ideas, and the test is if they are useful or not. But you cannot say, no, we don't need this because we have that. Well, you can say that, but then that's you are removing a possible thing that can be interesting. So you have a new idea, have a new concept, you test it. If the concept is not useful, doesn't give you predictions, does not simplify calculations, then you can say it's useless. So I don't bother with it. But here in this case, what I will show you is that the quasi-local mass and the Q scalars, they provide very distinct advantages, at least in computation. So that's why you take them. Anyway, in curved spacetimes, you have proper distance, area distance, can also define luminosity distance. There are several distances that can be defined. There are several volumes that can be defined also. See? And there are several masses that can be defined also. Right? Whether they're useful or not, you have to test it. Maybe they're not useful, so you don't consider them anymore. Now, answering your question, if we only use proper mass, we don't get very far, because the proper mass integrals cannot be evaluated in a simple analytic way, right?
So that's why we do it.
That's one reason. That's one reason to consider the other. Okay? So, definition. Let A be a smooth integral LTV scalar that is defined over a compact comoving domain. The associated Q scalar AQ is an LTV scalar that is defined over the same domain and that is obtained by the following through the following integral distribution. We have A, therefore AQ will be the volume with respect to will be this quotient with respect to the quasi-local volume, which is a proper volume with the weight factor and reduces to this form. The 4 pi have been cancelled, and the end product is this. Where here I have just evaluated these and canceled the 4 pi factors, and we obtain this. So this is like a machinery, grinding machinery. Every scalar, we construct this equivalent scalar, right? So let's see the density Q scalar, which we have just seen. We have seen this, right? Okay. Okay. But do you remember that we had already obtained something like this, right? Where we call this thing mu. On R, we also called it A. We use this parametrization. Therefore, our density, using the other parameters that we described in the Friedman, in the FLRW-like parametrization, what we see is that the Q density, the quasi-local density, is simply mu divided by AQ. Is this clear? Just changing labels and remembering the previous definition that we had. But before it was simply plain with symbols. Now we can associate a meaning to this thing new that we define. Specifically, now remember that A is 1 and big R is small r at our initial surface, right? That's the coordinate choice that we used. You remember that? Last class? Therefore, we can now identify the function mu. See, if we take mu is really the quasi-local density evaluated at T0. This is the initial quasi-local density. See? And therefore, we can write rho q as rho q0, which is rho q evaluated at the initial slice divided by this scale factor, right? This is the key issue. The mu that we defined before, right, was simply the quasi-local density obtained through this machinery evaluated at an initial time. Where is this initial time? It's arbitrary. You can put it anywhere. It can be the present cosmic time, whatever. Okay? And so we have now an interpretation for this quantity mu. And also we have the following conservational relationship. See? Because we can say that m is this quantity, right? It is, remember how we define m? We parameterize m in this way with mu here, right? You remember we did that? But then this is also equal to this thing, right? We've derived it. So what we have is that rho q times r cube is conserved by the fluid flow. Because even though rho q depends on time and r cube depends on time, the product of them is independent of time. Therefore, this whole product is conserved, is a quantity that is conserved by the fluid flow, right? Both functions independently depend on time. But if you multiply them, you get something that is independent of time and therefore is preserved by the fluid flow. That means if you compute it for an orbit, for a single orbit, then it will stay put. That quantity will not change on time. It's preserved by the fluid flow. It's preserved by the forward velocity. As the orbit is propagated by the forward velocity, this quantity remains constant, okay, for every orbit, okay? So, it's a very nice thing, very nice. Now, note, the Q scalar associated with a constant is the same constant. Obviously, if this is constant, if A is a constant, then it comes out of the integral, and then AQ is trivially equal to 8. Can you see that? That's evident, right? So the Q scalar, or the Q scalar of the constant is the constant itself. See? There is this definition, this machinery we are constructing. Constants are completely invariant to this. See? The Q scalar of a constant is the constant itself. Therefore, what would be the Q scalar of the cosmological constant? Well, it will be simply the cosmological constant, right? Now, notice also something. This is additive. That is, if A is the sum of B plus C, then AQ will be the sum of B plus, is this clear? This is additive.
Yeah, because it's properties of integration, sir.
Yeah, because this is not modified, and the integral is additive.
Yeah.
The integral of a sum is a sum of the integrals. And it's also, if I multiply times a constant, it's also invariant, right?
That means linearity.
it satisfies this linearity condition. Because, the average is a linear function. It satisfies these linearity conditions, right? So what we have is that the Q, see this transformation, the Q integral definition applied to a sum is the sum of the components, right? And so the cosmological constant is not affected. We can simply put the cosmological constant without any problem. Okay? Now let's look at the spatial curvature scalar. See, spatial curvature is the Ricci scalar of the surfaces orthogonal to the four-velocity, right? This is also a covariant quantity, because given a four-velocity field, we have three-dimensional surfaces, and the Ricci scalar of these three-dimensional surfaces is coordinate independent. So let's look at this. The Ricci scalar has this form. We are going to define this curly K, because the Ricci scalar always appears divided by 6. So instead of and also this horrible symbol with the 3 on the other side is very complicated. So to make notation simple, we're going to define curly K is going to be Ricci scalar divided by 3. And the formula is this. You can compute this with Maple. You take the three-dimensional surfaces. You can define in the metric file, you can also define three-dimensional spaces. Right? So you compute the Ricci scalar, and it is this thing, right? Therefore, notice that this thing is equal to this, right? Directly from the computation. Okay? Just passing this multiply. Yeah? You pass from here to here, right? Now, next step is, let's compute the quasi-scalar distribution. KQ will be this. So I'm just following the formula. But if you follow this, if you substitute this, you get this. So you get this. Very simple. Very simple. You would never be able to do this with a proper volume, right? Because the proper volume, this integral will have to be divided by 1 minus k. And then it cannot be but here, this is trivial because of the definition here. I think if you have doubt, you should do the intermediate steps by yourself, but this is fairly simple to do this, okay? Now, once we have obtained this, do you remember that we parameterized capital K in this form with a kappa function here? You remember that? Yeah?
Yes.
So R, big R, has this form. Therefore, the quasi-local spatial curvature is simply kappa divided by K squared. So now we can identify kappa as the initial quasi-local curvature, right? And we can write the quasi-local curvature in this very nice form, right? And then, since big K is equal to this thing, but it is also equal to this thing here, we can say that the quantity kappa K times R squared is conserved by the fluid flow. It behaves like rho Q times R cubed. And here it is KQ times R squared. This quantity is conserved by the fluid flow, just like the other one was, right? Yeah? Just very simple results, right? Okay, then notice that since R cube, rho q R cube, and K cube R squared are fluid conserved, right? And also we know that rho q0 is rho q times A cube, and kq0 is kq times A squared. These quantities are also fluid conserved. This quantity is also conserved by the fluid flow. And if we take the quotient, this quotient, how do we transform an exponent 2 into an exponent 3? We raise to the power 3/2, right? And so this quantity and consequently this one also are conserved by the fluid flow. See, this quantity is important because, as we will see later, this quotient generates growing modes of dust. But we'll see that later. For now, it's just a quantity that is conserved by the fluid flow. Okay? So the Hubble expansion scalar. We recall that the Hubble expansion scalar is this logarithmic derivative, right? We've seen this formula before. Therefore, h r squared r prime is simply 1/3 of the dot derivative. Here in dust, dot is the time derivative, the coordinate time derivative. Because for dust, coordinate time is proper time, right? Okay? So we have this derivative. Therefore, we evaluate HQ. HQ is this, but we substitute this and it is this, right? We just substitute. Okay? And then we evaluate and we can, this is a dot derivative, which is time derivative, right? And this integral is evaluated in the radial coordinate, right? So you can exchange the operator, the derivative, and the integral operators. You can exchange them. Why? Because the integral is along one direction, and the dot is along another direction. Therefore, if the integrand is smooth, you can exchange the derivative and the integral. And therefore, this thing reduces to this. But this is r cubed by 3 dot. And so once we do all this, we see that HQ is simply r dot by r, which is the same as a dot by a. So here we see that what we were calling H per is simply the quasi-local Hubble scalar, right? Okay. This is the scalar, the Hubble expansion tangent, the direction tangent to the orbits. Well, this fellow we can identify with the quasi-local Hubble factor, right? But the nice thing is that we already have seen that the quasi-local spatial curvature has this very simple form. Very simple form. And the one for the density had also very simple form. And we can see now that HQ has this very simple form, right? So the question now is to express everything we have done in terms of Q scalars. At the beginning, it might be just a formal exercise, but we'll see that it is that it has advantages, important advantages. At the beginning, at least mathematically, you have no doubt of what I've said, right? You might say, well, is this really necessary? Is this really useful? We'll see that. But at least mathematically, I'm not saying something incongruent like 2 equals 3, right? You understand mathematically what's going on, okay? So notice that the Friedman-like equation becomes very simple, because the Friedman-like equation we had before, we put here H perp. But we know that H perp is H cube, right? So our equation, our Friedman equation looks like this, right? This is the Friedman equation we had before. But now, instead of writing mu divided by A cube, we put rho q0, k q0. And this looks this looks identical to FLRW, except that in FLRW, this fellow here depends on time only, the scale factor. And rho q0 would be rho 0, would be a constant. Now here is a function. It's a function of r, right? And it's initial conditions. Now, notice also something. Suppose we are in an FLRW mode. That's, I think that's another important thing to notice. Suppose it's a Friedman-Robertson-Walker mode. So the metric is like this. This depends on time. Okay. Okay, this is FLRW metric. Okay, right? So, what's the density? The FLRW density is, right? What's the quasi-log? Well, okay, and what is the special curvature? Would be right, and Hubble factor, Hubble scalar, right? Now, we're using a metric, an LTV metric, that looks very similar. Our LTV metric is very similar . Okay, because remember that we have put here kappa, but now kappa we know that is the initial value function. Okay, and what is rho q? Well, rho q is rho q0 by a q. What is kappa kq? Is k 0. And what is HQ? Is A dot over A. So what the Q scalars are doing is that they manufacture, it's a way of manufacture LTV scalars. LTV scalars, they depend on R, that behave, that mimic FLRW scalars. Look how they resemble. But rather than invent them, we now can manufacture them, and we can identify them as quasi-scalar average distributions. We could have invented these scalars by prescription. I was dreaming and I invented a scalar. How did you invent it? I don't know, an inspiration. I had a lucky day, and I was inspired, I invented. Well, now we can say, no, no, no. We obtain these scalars by a definition, by a rigorous, formal definition, a covariant way of defining them, right? Because we're integrating over a volume defined for the orbits, right? And the quasi-local mass is related to a quasi-local density, and so on. But notice how this is, don't confuse this with this, because this depends only on time. And this depends on time and radius. However, the scaling laws are formally identical. So we manufacture LTV scalars that mimic FLRW scalars, right? And they are also related to a weighted average. In a sense, we can say that the quasi-local scalars, show that if you take an LTV model and you average the scalars with this weight factor, the so averaged scalars behave like FLRW scalars. Or an LTV model subjected to quasi-local average is like behaves like an FLRW model. Or FLRW models are average LT models, right? So, because what happens when you have something inhomogeneous and you average, you iron out all these inhomogeneities, because you substitute all these inhomogeneities by a single number, right? So this is achieved by the quasi-local average, not by the proper volume average. Well, we'll be seeing these things before, okay? I mean afterwards. I'm not traveling in time. We will see these things before. That sounded like time machine. Okay, so notice first thing that this is very important. Rho Q is not rho. This is not K. And this is not H. Very important.
These are all quasi-local.
This is not the density. The quasi-local density is not the density, etc. However, we need to relate them. We need to relate this and this. We need to relate this and this, this and this. Why we need to relate them? Because we know that the description of the models require that we know density, Hubble scalar, and special curvature, and then shear and psi2. So we have to relate all these scalars that we already know to the Q scalars, right? We have to relate them, okay? And for this purpose, we're going to define fluctuations. Why fluctuation?
And in flat case it would be same?
What?
In flat case it would be same?
In flat case, it will be the same, yeah. Flat case, yeah. And also, not only in flat case, but if we go to FLRW, they become the same.
Isotropy homogeneous.
Yeah, because as long, if you have an LTV model, and you make inhomogeneities very small, very small, very small, it tends to an FLRW model.
Yeah.
And then you can say that the Q scalars tend to the normal scalars. Or the opposite. The usual scalars will tend to the quasi-local scalars. The difference between them will go to zero. Yeah, that's true. Now, why fluctuations? What do people do with averages? Suppose I have the average weight of people here. Say, Suppose I have the average weight, and it's 60 kilos. And suddenly, a small man comes here and says, well, I'm only 20 kilos. So how do you characterize this? Well, you would say it's a very large deviation from the average, right? Now there comes a big fat guy and 200 kilos. Right? So, once we have an average, we can look at individual cases as fluctuations from the average. If fluctuations are very small, we can say that the weight distribution here is almost homogeneous. Like the heaviest person is 62 kilos and the lightest one is 59. Say practically everybody is the same, right? If 200 kilos and 20 kilos, and say there are large inhomogeneity here. So fluctuations are a measure of inhomogeneity. In fact, in statistics, these fluctuations are the moments. See? It's not the same to have a huge variance or a small variance. Small variance means that the Gaussian is almost very flat, right? And the huge fluctuation, a huge variance, is a small Gaussian, right? So this is important. The average only gives you a piece of information, but the interesting information are the deviations from this average, right? This is what allows you to make more informed statements, okay? So here, what we have is something, it's an average distribution, right? If we fix the domain, this average distribution can be the average, but it's only for that fixed domain, right? Okay, so it is interesting to see objects of this type, right? This is the scalar itself compared to its quasi-local average at each domain. See, we do this at each R. See? We do this at each R, right? This is a fluctuation. See? What does it mean that here we are in the center? See? Now, what's going to be the Q scalar at the center? Well, the Q scalar at the center is the same as the scalar, right? Because there is a, well, that's not so easy to see. This integral, okay, a r squared r prime dr r squared r prime dr. And we integrate from 0 to a very small number. 0 to a very small number. So basically, if we do this, we can see that a minus aq is of the order of epsilon. And if we set epsilon to 0, then they are the same. So at the center, they are the same. Now, we take a small neighborhood. Let's call this dA, right? Let's call this dA. So here we evaluate dA for this r. Let's say r equals 1, right? dA 1, okay? And it's something, right? It's a number. We obtain a number. Then we go to the next one. It's going to be r2. R equals 2. And we obtain another number, right? Because A and AQ are different. So their difference is also going to be a function, right? So this is what we're going to study, okay? Now, notice that here what we are doing, we're comparing A and AQ at each orbit. right? At each orbit, we compare these two things. And so we get a function that depends on the orbit. Depends on the coordinate r, small r, that is labeling the orbits. And of course, it also depends on time, because we do this comparison at the fixed time surfaces, but we do it also in the next, the next, the next, the next. And it will also be depending on time, right? Right? But this is what we're going to do, compare at surfaces, right? Okay? Now, notice the difference between this and the following. Here, this is the center, and we choose one orbit. We call it r equals r star. This is one orbit, right? So we obtain AQ at this orbit. Time is fixed. Time is fixed, but it's arbitrary. It can be fixed at any time. Okay? So, right? We take this one at this strictly one orbit. Not at all the orbits, but only at that orbit, right? Okay? And so, we compute for internal orbits here. Here we have R1, R2, in such a way that R1 and R2 are smaller than, okay? We take the internal orbits, right? And so we make this comparison. We make this comparison. We say A minus A, let me call this A Q star, right? Okay? Clear? Everything understood? Yes? Okay. So now we are going to compare A with AQX. So we are comparing this not with AQ evaluated here, but with AQ evaluated here. See, this is fixed. We fix the domain. And interior points we compare with this domain, right? Okay, we compare with AQ. So this, strictly speaking, is comparing something like this. Right? So this is a function of R and R star, because we fix this first. Why we fix it there? Because we want, it can be arbitrary. But once it's fixed, it has to stay fixed. Okay? This object is going to be different from this one, because here we are doing this comparison. Right? Here we're comparing at each point. Here, we fix this, and we're comparing inner points with the one that has been fixed, right? So this is a function. This is a function of R. This is a this we're going to call non-local fluctuation, and it's going to be a function of this. Right? Now, these two only coincide at the border. This non-local fluctuation coincides with a local fluctuation only at the border. Because what happened at the border we have DNL is A star minus A Q star, and is the same as the local fluctuation evaluated at star, right? At the boundary they coincide, but inside the boundary they don't coincide, right? These are non-local fluctuations, and these are local fluctuations. Meanwhile, we're only going to see, well, in fact, they're not local, are quasi-local and non-local fluctuations. See? This is a strictly non-local. Why is non-local? Because this quantity here, AQ star, is a number that is associated to a whole volume. So we take inner values and compare it with this non-local value. And the other one is quasi-local because we are computing and comparing at each sphere, right? But we compare with the same sphere, right? Okay? This is crucial, very important difference, because when we fix this AQ star, it's really the volume, it's really the average. The average is only makes sense if you fix the domain, right? See, the average weight here is 60 kilograms, but this is a statement that pertains the whole group. If we put extra people or somebody leaves, then that average has to be recomputed, right? So, but fluctuations around this average are valid as long as we keep the volume. See, I can say he's a fluctuation of whatever, and she's a fluctuation of whatever, but it's referred to this group, right? If he goes out, then the fluctuations have to be recomputed, right? The average, etc., right? So, as long as we keep the fixed domain, which can be arbitrary but has to be fixed, we can make local comparisons with this average, and then we have non-local fluctuations, right? And on the other hand, if we have a group that is changing, say, then we have the other situation. But in the other situation, we are comparing the fluctuation, say, at each sphere. We are making the comparison between the average obtained at a given sphere and the local value at the boundary. See? I mean, these are quite evident, the differences, but they're subtle. Now, for the time being, we're only going to consider the quasi-local fluctuations, not the average. The average ones, we will see them also later, right? But for the time being, we will consider fluctuations that compare A and AQ. Okay? Clear? Understood? Now, why these things will be helpful? Because, let's say the fluctuation of density. Fluctuation of density will be defined this way, right? Okay? What is this useful for? Well, it is useful because once I know this fellow, and I know this fellow, I know this one also. See?
How you can know deviation?
We'll see. They have properties.
Okay. Because without knowing rho, how yeah.
No, but that's the point. We already know how to compute rho cube. We have a formula.
Yeah,
for it.
that is okay, yeah.
We'll find a formula for d rho,
Okay.
and then we will be able to compute rho. That's the trick. But what we're going to see is that it is easier to compute this two than to compute this one, right? And what we will see is that these ones have FLRW mimic forms, and this one mimic perturbations. That's the nice thing about that. Yeah, and it will have non-trivial connection with perturbation theory. See? Powerful, powerful things. Lots of window users don't realize that. They keep on doing Windows, but they don't know what's to have a nice computer. Following that analogy. How much time we have? 10 minutes. 10 minutes? Okay, I think enough time to see this. Okay, Q-scalars different from standard scalars. How we relate them? Well, we define local fluctuations. Really, they're quasi-local, but it doesn't matter. Don't worry about it. See? We can also define this type of fluid. These are, see, because notice that dA has units of density, right? Has the units of A. Whatever units A has, dA will have them. But we can construct dimensionless by dividing, see, it is a fluctuation, the D itself divided by the AQ. We call them relative fluctuations, or we can call them exact perturbations because they look like perturbations. But I'm afraid to use the term perturbation because whenever you say perturbation, people assume that it's approximated. No approximation here. Anybody who says approximation goes out of the window. No approximations here, no perturbations. This is exact, okay? It's not that they are linear, non-linear, third order. No, they're infinite order, they're exact, okay? Now, notice that the standard covariant scalars, we can derive them in this way. This is what I just said in the blackboard, right? All Q scalars satisfy the following properties. See? These are the keys. Like, once we have AQ, if we derive it, then it's going to be something like this. And if you perform all these derivations here, it's very simple. You derive this thing first, and it's multiplying the integral. But the integral can be related to the Q scalar. And then you multiply this times the derivative of the integral. But the derivative of the integral is the integrand. So this is very simple to obtain. So here you have this property, right? This is the radial gradient property of the Q scalars. Then there's another property. Integration by parts. If we integrate this thing by parts, we obtain this formula. So this is also a relationship. See, notice that these are algebraic relationships between A and AQ. I can relate A and AQ through the gradient or through this integral. Which one to use depending on, both are available depending on the problem, right? So do that, then this fellow here, notice that this is the fluctuation. So this fellow here will be simply, we divide this by this, right? Or we use this integral. So here we have a formula to compute the fluctuations, a direct formula. See? Once we have the Q scalar, we do these things, or this thing, depending what is, well, here you would need the gradient. Here, notice that you need the gradient of the Q scalar. And here you need the gradient of the scalar itself. So essentially, what all these things show is that the fluctuations are very responsive, very dependent on the gradients of the scalars. Which is interesting because notice that here, the difference between this, the FLRW density, and the Q density is the fact that the Q density depends on R. If I take the radial gradient of this, it's zero, trivially zero. But if I take the radial gradient of this thing, it's not zero. In fact, the fact that the radial gradient of this is non-zero is what distinguishes this object from this one. So essentially the fluctuations are telling you how different is the LTV model from an FLRW model, because they are related to the radial gradient, right? If the radial gradient is zero, see what you can see here. If the radial gradient is zero, then dA is zero. And and delta A is also 0. Delta A is the same thing, it's just that here's a Q. Here's a Q, here there's a type here, there's a Q. So what happens if the radial gradients are 0? Then dA is 0. And if dA is 0, then A is the same as AQ. Right? So the fluctuations are telling you are gauges that are not gauges, are like measurements of the inhomogeneity. Because they tell you how homogeneous is the model. Right? So once we are equipped with these properties, then there's a lot of things that we can do, but we will do them, well, let me announce it. Let me announce what we're going to do. Well, in subsequent sections, we'll see that there are several representations of Q scalars. Now, we have evaluated rho Q, KQ, and HQ. But we can obtain other representations. We can construct omega factors that are Q scalars, right? So we can work with several Q scalar representations. There's not a unique one. There are several ones that we can build. And which ones to use? Well, it depends on the problem. Like if we are doing a cosmological problem, it might be more practical to use the omega factors defined as Q scalars rather than density and spatial curvature. Depends on the problem at hand, but we can do there are several representations of Q scalars that we can do. Another point, the Q scalars and their fluctuations satisfy, they are covariant, coordinate-dependent objects. See, I will show you that they are not, they are defined in a covariant way through integrals that are evaluated along orbits, and that the quasi-local mass has a connection with Schwarzschild mass, etc. But also, once we compute them, I'll show you that they are directly related to invariance. So they are also coordinate-independent objects. Then they completely determine the dynamics of the models, either analytical or numerically, and they do so as a dynamical system. So once we have a set of Q scalars and their fluctuations, the models are determined. And they can be determined analytically because we can find scaling laws for them, or they can be determined numerically by evolution equations for them. These evolution equations, we will find them through the 1+3 system. The 1+3 system, in terms of quasi-local scalars and fluctuations, reduces to a dynamical system because we will see that the constraints become algebraic. Okay? And then the Q scalars are LTB objects that mimic analogous FLRW quantities, while the fluctuations convey the information on the inhomogeneity. And therefore, they are analogous to perturbations, but they are exact quantities. When do they reduce to perturbations? If we go to the linear limit. If we go to the linear limit of the evolution equations, we reproduce the cosmological perturbations in the comoving gauge. See? And the Q scalars can be related to scalar weighted average, whose back reaction is identically 0. That's another interesting thing that will come out in the next lectures. And also, the Q scalar and their fluctuations are more useful than the standard LTB variables when undertaking their application to various theoretical issues. For example, I've been back reaction. What is back reaction? Back reaction is supposed to be nonlinear effects on the evolution of overdensities and inhomogeneities when you study their averages. When you study the dynamics of averages, you obtain nonlinear terms that are interesting to study, right? So even if I don't use the quasi-local average, but I use the standard average, quasi-local scalars are much more useful than the standard variable. Another problem, gravitational entropy. Gravitational entropy it's an open theoretical problem. I'll talk about that. But to study this problem using the traditional variables is horrible. It's horrible, absolutely horrible. People do it because people are hard-headed. Yeah, I've been like, for example, had a colleague, Polish colleague, very nice guy, came to Mexico. We started working on this, and all the theoretical things we did in quasi-local variables. Suddenly he took care of the numerical methods, and he went back to the same clunky, horrible variables, which make the numerical work much more complicated. And I asked him, why do you do that if we have a dynamical system? He said, well, all my codes are in Fortran and are already in this variable. I don't want to rewrite my codes. It's like you take a Windows user and the old Windows. Why are you using this? Well, because I'm used to it and I don't want to learn anything new. I don't have time. Publish and perish, publish. Don't have time. So hopefully, since you are not vitiated by these things, you might, in case you do research in these areas, you might use these variables as well. They are really good for numerical work. They are really good. And also they are very good for theoretical problems. Now, if you are only observations and you are this empirical dogmatist and you want only to produce, then, well, and if you have a mountain of codes in Fortran written, then okay, then perhaps not going to bother about that. That's the case with most of my colleagues who work in this. They understand, they like them, they say it's useful, but when it comes to do the hard work, they go back to the other one. What can you do? Okay, so we continue tomorrow. Okay?
Tomorrow test? Fine?
Yes. Yes, sir.
Tomorrow is test. Or you want on the day after?
Tomorrow.
Any day is a good day.
Any good day is...
No, because tomorrow I'm not in. So I'm thinking the day after tomorrow. Day after. Because if an exam conduct करना है हमें बहुत बड़ा problem. I'm not here today. Tomorrow may not. I mean I can come, may not come. Kuch uncertainty है tomorrow. So let us take day after tomorrow or 22. 22nd both day. Okay. You get 1 day.